Good afternoon. I am Sachita and I will be talking about my proposal on mice brain tissue characterized by 2D seeded laser-induced cavitation with color-changing photonic crystals. Cavitation is the sudden, unstable expansion of a void or a bubble within a liquid or solid. While predominantly studied in fluids, cavitation is also known to be the origin of damage in soft materials, including biological tissues. For example, strong evidence suggests that cavitation occurs in brain during sudden impacts, leading to traumatic brain injury, or TBI. Characterizing the high strain rate mechanics of soft materials is critical to understanding the complex behavior of various dynamic injury mechanisms, including traumatic brain injury. It is clear that a broader, deeper understanding of cavitation within soft solid is necessary to help navigate the complex paths that lead to damage in the brain and other soft tissues. To address such challenges, we investigate an experimental method which allows quantification of extreme mechanical properties of soft materials using ultrafast imaging of highly reproducible laser-induced cavitation events. Such understanding will lead to new strategies not only for mitigating damage, but also for using cavitation as a therapeutic or diagnostic tool. Here we demonstrate a 2D seeded laser-induced cavitation or SLIC approach in which a mouse brain is sectioned to reduce the optical path length, and the slice is confined by two glass plates with ablation seats. As a result, the digital image correlation or DIC technique can be applied to the in situ SLIC image with a reference or pre-SLIC image for mapping of displacement vectors of the rapidly deforming slice. Since brain tissue is an anisotropic material, you cannot fully derive the impact stress from the mechanical properties just by SLIC. In order to measure the mechanical stress during the cavitation, a stress indicative material can be employed during the cavitation event. For example, a metamaterial like a photonic crystal which changes color when subjected to deformation. Cavitation shock wave exposure of sufficient intensity disrupts the 3D ultrastructure in a precise fashion. When the structure is disrupted, the color is changed or lost. Moreover, the degree of nano and microscale structural damage and hence color changes, which may be tuned based on shock wave characteristics. A layer of photonic crystal around 6 micron thick can be coated on one of the cover glasses, which will confine the brain tissue for SLIC characterization. We can correspond color changes in photonic crystals with changes in stress induced by cavitation events. Thus, we can correlate the tissue displacement measured from DIC with the stress applied to tissue measured using the photonic crystals. Photonic crystalline colorimetric properties are an inherent consequence of the periodic modulation of refractive index arranged in 3D, where interference of the light waves lead to stop photonic band gaps. This results in light of a particular range of wavelength being totally reflected in a photonic crystal. Briefly, when light arrives at the surface of the periodic structures, it is strongly reflected by constructive interference between reflection from different interfaces of alternately high and low refractive index, resulting in so-called structural color. In particular, we can use this colorimetric change in custom engineered photonic crystals based on the dynamic exposure and correlate this color shift with ultrastructural changes and damages on brain tissue. Thus, future studies will directly calibrate these color changes to unique cavitation-induced injury. However, several long-term challenges remain before this technology can have widespread implementation, like the fabrication of photonic crystals that exhibit color changes within the appropriate dynamic range of stress experienced during a cavitation event might require extensive optimization. Also, accurate color imaging the micron-scale photonic crystals might be challenging due to their size. Thank you.